Hello, welcome to episode 3, Laws, Causation, and Mechanisms. So this is the third of the 3 videos on the topic of regularities and laws. All right, so the overarching themes that we've already seen in the other 2 videos are going to sort of come to a new kind of conclusion in this particular video. So we've been discussing mathematics as a language in which to express laws. And in this particular video, we're also going to consider the rejection of the kinds of implicit or explicit requirements that science must have mathematically formulated and in particular universally true laws in order to count as a science. We'll discuss laws as capturing something about modality, so how some things happen for reasons that are more than mere accident or coincidence. And we will also, in this session, be looking at causation and mechanisms as involving less necessity than laws, but still more than simply being an accident. We're going to talk about, we have been talking about laws as a locus of inferential connections as part of a theoretical system that hangs together. But what we're going to see today is that there are sciences like biology that really have fewer, and in some cases may not have any such theoretical packages. So then we have to sort of confront, do they have laws, or do laws play some other kind of role in such sciences? Instead of a distinction between the phenomenological versus unificatory or fundamental laws, we're going to find that now it might be something more like top-down versus bottom-up generalizations that replace laws in sciences like medicine and biology. And instead of focusing on the sort of contrast between concrete and observable regularities and the underlying simplicities, sometimes it really is the complexity and not the simplicity that we're interested in the case of especially things like biology. All right, so we will then conclude by coming back to this topic of describing versus explaining regularities and compare laws to mechanisms and causation for that particular point. All right, so now we're going to get to the section where people got very dissatisfied with laws, and they're looking for alternatives or supplements to laws. So there really was, since about the year 2000, a huge shift in philosophy of science, where there was a rise of what I'm going to call non-law-based explanations in philosophy of science. So focus especially on causation and mechanisms as a primary driver of much of the explanatory resource in the sciences instead of laws. So these involve some degree of modality in the sense that they're capturing something about the world that is regular, even if it's not as universally regular as like the law of gravitation, and that has some degree of non-accidental or non-contingency to it, but it's still going to be weaker than many of the kinds of laws that we've been looking at so far from physics. So there's some regards also in which these have been conceived of as supplementary to laws. So laws involve this higher degree of necessity and rule out certain kinds of events or relationships. They say, here's the bounds, and within the bounds it's possible, and outside of the bounds it's impossible. But then within those bounds, we still want to know further things about what actually happens. And there's still further regularities that are maybe more contingent, but not completely contingent, that we would like to be able to talk about. And so that's where tools like mechanisms and causation can fill in further details. So there's other regards, though, in which these new developments have displaced laws. So causal relationships in particular can range in probability up to probability 1. And to say that something is probability 1 just is to say that it's necessary that it happen. So what used to count as a law can in many cases now be considered or written or expressed as a causal relationship instead. So we'll then look at new accounts of laws, in particular, pragmatist and neo-Humean. That's supposed to say neo-Humean. My autocorrect does not like the word Humean. All right, so if you remember the deductive nomological model of explanation from the first video, there are laws that figure as a special kind of a premise in a deductive argument of the thing to be explained, which is called the explanandum. So this deductive argument has to have what's called a covering law somewhere in there. And it has to be more general than the specific thing that is to be explained because it covers it as an instance. So if you say all F's are G's, the all F's are G's is the covering law. This is an F is another premise. And then the conclusion is this is a G. So you can deduce that this is a G from those first two. So the way in which Hempel and Oppenheim talked about laws had causal laws as being the ones that are deterministic. So they had to have, as it were, probability equal 1, so 100%. Premises that involved any kind of probability were considered part of the inductive statistical explanation. So if you had a law that said 95% of Fs are Gs, this is an F, therefore this is a G, then you would have an inductive statistical explanation, because there's always that 5% chance that it could be an F but not be a G. All right, so we already discussed a lot of problems with this deductive nomological account, and now we're going to use those to sort of launch us into the more contemporary discussion. One of these problems leads to improvements in using probabilistic relationships in explanation, eventually leading to causation. So we got better and better and better at talking about correlation and when correlations between things can explain one of them, before we eventually figured out what we needed to add to the correlations in order to get to causation. The other major sort of concern that we're going to follow up on is the development of alternatives to laws for explanation in biology. So that's especially going to include mechanisms. All right, so probabilistic changes, as we discussed before, are when the thing that's doing the explaining, the explanans, raises the probability of the explanandum. And the idea is, if it raises the probability of it, then when that occurs, we have the explanans for why it occurred. The problem was that you could have something that was only 2% likely to occur on its own, and then your explanans is something that raises it to 5% likely. That's still not especially likely to happen. And so it seems like there is something that needs to be said in addition to simply changing the probability. So there were progressive refinements to this, and part of what came out of those progressive refinements is that sometimes you can have two variables that are probabilistically correlated in really reliable ways, because this one causes this one, or because this one causes that one, or because they're both caused by some further variable. So if something up here causes both of those two, then they are going to be correlated with each other. So if A causes both B and C will be systematically correlated, even though neither of them cause each other, because the presence of one indicates that A took place, and so that B took place raises the chances that C took place, only because we know from here that A took place. All right. So we want to kind of come up with a way to say, no matter how tightly correlated something is, there's some further thing that we can use to distinguish between very high correlation and actual causal relationships. So this led to a big breakthrough where there's now an actually technically defined term that is intervention, or sometimes referred to as doing, or the do operator. And it's not used in the sort of common parlance of, I went and did something today. It's like an actually defined term for what you can do when you're modeling with a system of variables. So we'll get to that. So one of the big turning points here is a really funny example that comes from Nancy Cartwright's paper, Causal Laws and Effective Strategies. So she got a letter in the mail that said, well, it wouldn't be true to say that buying a life insurance policy from us is going to increase your lifespan. Nevertheless, it is true that holders of our life insurance policies have, on average, longer lifespans. And she latched onto that as like, both of these are true. It's true that buying it is not an effective strategy for increasing your lifespan, even though it's true that people who have this also have a longer lifespan. And so she was able to sort of get across the idea that what you want out of a causal law is more than just prediction. So correlations can give you really good predictions about what you're going to see. But what we're often more interested in with respect to causation is being able to bring something about or prevent something from happening. So we don't merely want to be able to predict what our own lifespan is. We want to do something so as to lengthen it. So we want to have some sort of effective strategy. And so she wanted to say that causal laws are not just the ones that are deterministic per the deductive nomological account. Rather, causal laws are those that we can use to do things with. So we can sort of change the future rather than merely foresee what it's going to be. And this really shifted the discussion. And then there were two extremely influential, very technical books that came out in the year 2000. And then a book that was offered as a sort of semantics, interpreting the very formal approaches from those the two books in the 2000s. So if you were to start reading somewhere, probably the Woodward would be the place to start on this. And now we have this introduction of the technical term. So for Pearl, he calls it the do operator. And the do operator is a special way of modifying the values that a variable will take. So we'll get to this in a second. In the Sperdes, Gleamer, and Shinies, and in the Woodward, it's more often called an intervention. So you intervene in a very specific and well-defined way, and then you can tell the difference between variables that are correlated and variables where one or the other causes the first. All right, so this changes the notion of definition, or the definition of causation, in a very it's not unconnected to the historical discussion, but it takes it away from an emphasis on individual, this particle bumped into that particle and caused it to go over there. Takes it away from what is called token causation. So individual happenings that are causally connected through time and space, to what's called type causation, or also often called variable causation. So then you can say more general things like smoking causes cancer, and you have smoking on the one hand as a variable, and you have cancer on the other hand as a variable. And there can be lots of different instances of smoking and lots of different instances of cancer. And it's not the case that every instance of smoking is going to lead to an instance of cancer. Nevertheless, we can perform tests on these two variables to show that, in fact, even though some people who smoke don't get cancer, smoking is, in fact, a cause of cancer because of the way they behave together. So we're moving to what's called variable causation. So this is what's called a directed acyclic diagram. And these are actually quite useful in discussions with scientists. I've found that even people who haven't been exposed to this, find it very intuitive to use this as a representation for their variables and help people sort of think out loud more clearly together. So we'll treat each of these nodes here as a variable. So we've got A, B, C, D, E. So we've got 5 variables, and we've got causal connections between them. So you can see that A has no causes in this graph, is how we would say it. There's no arrows coming into A. We just start with A. And it's worth noting that this isn't supposed to be an exhaustive description of all the causal structure that could possibly be involved with the system in question. It's more like, I'm working in a certain kind of scientific field. Maybe I'm trying to map out the sort of the circulatory system of the kidneys. And I have a certain set of variables that I can measure. And we call that, this variable takes a certain value at a certain time. So I would define A as maybe the heart rate. So how fast is the heart beating? And that's going to be something that has, it can't be beating at negative numbers. It can't be beating at like numbers above 1,000. So there's a certain range that's now set out as what the values are that this variable can take. And then it influences lots of other things. So in this example, if we just look at B and C, we'll see that they are probabilistically correlated with each other. So if B occurs, it's more likely that C occurs, and vice versa. If C occurs, it's more likely that B occurs. But that goes away when we do what's called conditioning on A. So if we say, we know that A occurred, then B and C are no longer correlated with each other. Similarly, we can tell if B and C are directly causally linked by performing an intervention. So an intervention is what we call exogenous to the system. So I have to set the value of one of the variables that I'm intervening on to a very specific value. So I have to say, I want B to take one exact value, maybe within this certain sort of range of blood pressure. And so I know that I have to sort of shield it from what usually makes it take its values. And so I have to use some sort of intervention to poke at B, as we call it, and then think of it like an arrow that comes in from the outside of those. I can't use A or any of those other variables to perform the intervention. So you perform an intervention on B by requiring it to break all the incoming arrows. We would put a little X over the arrow from A to B. So you've then made it so that you're the only person with a control knob for B. So the intervention is now the only thing that controls the value of B. It's no longer being controlled by, in this case, A. And so then you set B to a certain value, or you sort of wiggle it between different values. And once you've performed that intervention and broken all of the incoming arrows, then what you see is that when you wiggle the value of B, the only further variables that will have their values change are the ones that are causally downstream of B. So if I intervene on B and I wiggle its value, C is not going to change, A is not going to change, but D will wiggle and E will also wiggle because D is wiggling. So you can tell what's causally downstream of B by breaking the incoming arrow and wiggling its value. So that's why the intervention allows you to go beyond just the correlations or the probabilistic relationships. And you can hopefully get a sense. It's really fun to play around with these because there's a lot of things that you can represent and suddenly get more clarity on by using this kind of diagrammatic structure. All right, so this is a really powerful way to convey the modal content about what would be different under specific circumstances. So if B were to take this value, here's what would change about the other variables' values. So it's sometimes called a counterfactual account of causation because you can say things about what would happen under circumstances that are counter to fact. So not the circumstances that actually obtain. You can say, well, if B had taken this higher number instead, then here's what would have happened down here. So that's the kind of modal content that a lot of laws were taken to be doing before. What would happen under a variety of circumstances would, So much of what laws were earlier taken to be doing in describing or explaining regularities can now be captured using these causal relationships instead of law-like relationships. And sometimes they do an even better job because you don't have to distinguish in a graph between the causal relationships that have probability 1 of obtaining, so the necessary ones, and the causal relationships that have a probability of, say, 0.8 or 80% chance of happening. So you can just chuck them all in there, and they all sort of behave the same way. So in that regard, you don't have to take the ones that are fully necessary with probability 1 and sort of give them their own special treatment and then take everything that's less than probability 1 over here. You can put them all together. So despite that, causation has not completely displaced laws. And this is a contemporary topic that it would be fun to have more discussion of. Especially with respect to fundamental laws, the same content cannot be expressed using causation. Because you can't intervene on the variables in a way that shields them from influence from the other variables to which they are lawfully connected. So if we have some sort of fundamental law, or maybe like A times B equals C, we can't intervene on A via some other method from outside by shielding it from, for instance, the values that B and C take, because it's physically impossible for us to do so because it's a more fundamentally lawful relationship. So the variables can't be treated in this interventionist way. So they're sometimes even definitionally connected. So there's a way in which this also fits into what we saw with laws being the sort of thing that provide the outer bounds beyond which is impossibility, but within which you have a lot of other things that you still might want to say and you might want to be using causation for. So it's sort of like you've shrunk the gap in which the laws can figure into a much smaller territory, but it hasn't gone to zero. All right, so one of the other major trends has to do with laws, especially with respect to biology. So insofar as we were expecting or hoping that our laws would be universal and true generalizations, it doesn't look like biology has anything like that. Well, for biology, there's very famously, if you took the, I don't know, if you ran the tape, as they phrased it, of life, if we sort of went back, 3 billion years and sort of let things go again, then we would come up with probably a very, very different distribution of actual organisms that would evolve by this point in time than the ones that actually did. And so you think that the history of life on Earth has a kind of deep contingency to it that is definitely not universal in character. I'll also note here that around this time, they were also discovering, Nancy Cartwright again, that even in physics, you really don't have laws that looked like the deductive nomological laws. So if you had those sort of universal generalizations, they were usually literally false. They weren't describing what actually happens. They were describing, they were performing some other kind of a role. So you could either have something that was true, in which case it's not really generalizing, or you could have something that was a universal generalization, but not literally true. So even for physics, it didn't work well. So there's two lines of response here. If you're like, we're very dissatisfied with this view of laws in science. One is to reject that view of laws and develop a new view that does account for what happens in biology. So we'll get to this at the end. This is something like a pragmatist view that's more sort of bottom up with respect to generalizations, rather than what we'll see as top down, as universally true from which you derive specific instances. The other option is to just reject laws. Like, okay, if that's what laws look like, then biology doesn't have any. But biology is clearly doing some explanation, so we should talk about what it is that it's doing if it's not involving laws. So then you develop an alternative account of what explanation in biology and related sciences. So this will include neuroscience and medicine and economics, lots of other fields. So the year 2000 was a great one for as a turning point for this. And that's when a very influential paper called Thinking About Mechanisms came out. And this paper connected to the mechanistic discussions from the early modern era in natural philosophy, but wanted to say, look, really what we want to do is describe and explain the regularities that we do find. So we don't find regularities that are so universal that they cover all times and places. Nevertheless, we find things that are more regular than just individual instances. And when you find anything that's more regular, you kind of want to take advantage of that, because that's where you can get some really interesting science done. So you still want to be able to describe those, but you also want to be able to explain, why is it that this regularity holds and when will it cease holding? So that's what mechanisms were offered for. So the technical definition of a mechanism: mechanisms are entities and activities organized such that they are productive of regular changes from start or setup to finish or termination conditions. So there's been some proposed modifications to this, but this is still a really good definition of what a mechanism is. So I've bolded and italicized the key parts so that we can just kind of identify the important role that each of those are playing. So this is considered a kind of definition. So what constitutes a mechanism is anything that meets these criteria. That's what the R is for. And the entities and activities are what they call a sort of dualistic ontology. So there's little things that are best thought of as bits of stuff, but they do things. So we need both the objects and their particular, say, shape and their chemical properties and things like this. But we also need the activities that they engage in. And they're engaging in those activities often with some other object. And so what you get is this kind of organization. So this entity is doing something that influences the entity next to it, or spatially next to it, or temporally after it, and then it does something that influences the next and influences the next. So it's kind of like a chain of mechanisms. And it matters that it happens in a certain order. So they have to be spatiotemporally located in the right way so that they can interact with each other. So these interactions, when they're organized, are productive, in the sense that they succeed in producing some sort of change. Sometimes they produce a literal product. So you have like the Krebs citric acid cycle in the cell that produces extra ATP, or units of energy, for the cell. And it's also productive of regular changes. So you might have a mechanism for a stoplight that is productive of regular changes, namely like a predictable cycle in which the lights go from red to yellow, or red to green to yellow, etc. And then one of the other final and really important parts is the start or setup and finish or termination conditions. So mechanisms aren't supposed to just be any causal chain that you can find. So if you think of like a Rube Goldberg machine that's got really rickety sorts of setup, it might only work once, and then it's sort of, you know, the candle flame burnt up some key piece and now you can't do it again. So mechanisms are especially interesting sort of loci of regularities in science, precisely because once you get into the right startup conditions, it sort of triggers this little chain of the entities and activities in their little organized states, and it just goes until it reaches the conclusion of it. And once again, the Krebs citric acid cycle is a really good example of this. Once you get the right kinds of materials here and the right kinds of cellular machinery that's ready to go, then boom, you've now started one cycle of the Krebs citric acid cycle. And the diagrams that you see for that take you through, here's an entity and the arrows are showing, oh, it's passing this product on to that one. And you can often find out further, how exactly does it pass it onto there? Well, there's usually things having to do with the shape of particular macromolecules. And it goes all the way through and it stops when it has produced those extra units of ATP. So it's got a sort of like semi-self-containedness to it. Once it's triggered, it kind of goes pretty regularly, and then it stops when it finishes its stuff. And so there's causal things that happen leading up to it, and there's causal stuff that comes out of it, but it's got this kind of self-contained structure to it that makes it a really great target to find. So you can describe the regularity as a mechanism doing something, and then you can talk about what it is that helps that mechanism do those sorts of things. So we have two diagrams here. The top one might be, so the top one is very generic. So those are just standing in for all sorts of entities. So you have some phenomenon in that black box on the top that might be the production of energy by the cell. And you're like, whoa, cells can regularly produce energy. That's our phenomenon to be explained. So this is some sort of regularity that we now want to say more about. And so you can give an explanation for it by dropping down a level. That's what those dotted lines are for. And you're like, ah, here is some kind of input that triggers the starting conditions. And then it leads to a little cycle, and then it concludes, and then you're sort of out of the mechanism. And then you can say, ah, I'm very curious about this particular stage of the mechanism when this little X is sighing. So when this entity is engaging in this particular kind of activity, because the same entity might engage in different activities, then I can also go down a level and say, ah, but here's the mechanism for that process right there. So you can then sort of connect a lot of scientific knowledge at different levels of organization using this kind of way of connecting them into mechanisms. So here's an example from Carl Kraber's book on philosophy of neuroscience from 2011. So you've got some phenomenon where there's mice that are capable of navigating this water maze, and you're like, aha, this is our regularity, we want to talk about it. And you sort of give a mechanism for it that involves the hippocampus generating spatial maps. And that can't be the only thing. As you'll see, there's, you know, other things that could be going on, but that's going to be part of the mechanism that sustains and explains that higher level phenomenon. But then the hippocampus generating the spatial maps itself can be treated as a phenomenon for which there is a supporting mechanism underneath. So the neurons that induce long-term potentiation, you're like, ah, okay, but wait, how do neurons induce long-term potentiation? Well, and then you go down another level. So hopefully you get a sense of how an explanation that's given in terms of mechanisms can work. And there's no laws here at all. All right, so there was, of course, a debate about this. You could think that laws describe the phenomena. So they're the descriptions that pick out what's regular. And then the mechanisms do the explaining of why it is that this regular phenomenon holds. And in that sort of case, they would kind of supplement rather than compete. But at the same time, the mechanisms would be more fundamental. So for any law you could find, there would be a mechanism, as it were, underneath it that would give rise to or explain it. Or you could go the other direction and think that the connections between those stages, so what we were sort of putting in as those arrows, the activities in which the entities are engaged, are law governed and law sustained, such that if you go down with mechanisms, eventually you'll hit a place where there's no further mechanisms and you just have laws. So, you know, when you keep going down, for every law, does there have to be a mechanism? For every mechanism, does there have to be a sustaining law underneath it? That's kind of the debate. On one view of mechanisms, especially the McLemore, Darden, and Craver one, mechanisms are really useful exactly because they just don't answer these questions. So when you're actually talking about the mice that are capable of navigating the water maze, you don't want to have to go all the way down to particle physics every single time. And in particular, if you do feel like you have to go down there, most of what you discover is completely irrelevant to what you started with. So they claim, and I think this is very apt as a description of science, that at a certain point in time, you've just bottomed out. Like if you go any further down, you're no longer illuminating what you started with. You sort of changed the topic. So certainly there's things down there, but they're not anymore part of the explanation of what you started with. You could change what you wanted to have explained, but it wouldn't be an explanation of the thing that you started with. However, on the other hand, you could be a philosopher and you're like, no, we have to go all the way down and figure out what's down there. And this is an issue that, of course, David Hume, beat us to. So here's what I think is the best quote on this. "It is confessed that the utmost effort of human reason is to reduce the principles productive of natural phenomena to a great simplicity, and to resolve the many particular effects into a few general causes." And this really fits into the view of laws that we saw in the first video. But as to the causes of these general causes, we should in vain attempt their discovery, nor shall we ever be able to satisfy ourselves by any particular explication of them. These ultimate springs and principles are totally shut up from human curiosity and inquiry. So Hume's view seems to be different in different parts of his writing, but in this particular sort of longer passage from which this quote is taken, he seems to think that when you get down to a certain state, you're just stuck with a brute description of what's happening. There is some secret spring or hidden principle underneath the fabric of the universe, but you can't get there because, you know, it's under the fabric, it's covered over. And so in some other places, he talks as if he doesn't think there is any such thing, but in some places he talks as if it's there and we just can't know it. We are forever prevented from knowing about it. So the best that we can do is kind of get down to that, and then we're sort of, our spade is turned, as he puts it. So if the connections between the parts of a mechanism are causal, let's say, and then these causal connections can be explained by something at a lower level, something that's in a smaller or simpler mechanism, and so on down to the most fundamental level, do we end with the mechanisms or do we end with the laws? So it could be that the laws are kind of what we call brute. There just is a description of what holds. It has necessity associated with it. It's like, no, this is how it has to be. It can't be this other way. They just hold, and that's it. We don't have any further ability to give an explanation of it. Or it could be that the laws themselves could be given a further explanation, but we have to turn away from more empirically oriented things like mechanisms and instead have recourse to perhaps mathematical explanations of why, if these are the laws, then here's a mathematical reason why you couldn't do the thing that you're, trying to do. And it could be that necessity runs out. It could be that once you get down there, it's just contingent. And it's only at these sort of higher levels that you have regularities that have a kind of modal status of non-contingency associated with them. So we'll get to that with the neo-Humean accounts of laws. All right. So neo-Humean accounts of laws sort of take a different approach. They reject modality as it has been discussed so far, including all of the historical stuff. So there are things that go together. They're sort of constantly conjoined, but they're not necessarily connected. They just happen to be that way. And there's this sort of, it's a very metaphysical view. It's not one that comes out of the sciences. It's more one that I'm putting the neo in front of it because I don't think Hume holds this, but it's often called a Humean account, where you just say, look, there's just stuff that's happening and it's out there. You've got this manifold of space-time that has different properties in different regions of space-time. And what the laws should do is let us describe as much of that as possible, but not in a way that renders it necessary in a metaphysically deep way. So laws are definitely doing descriptive work, but they're not explaining why any particular thing happens. Things happen, and that's what we were referring to earlier as brute. Just brutally, there's a distribution of facts through space-time, and the laws just describe what that distribution is. So the laws on the neo-Humean accounts, including the best systems account, are the most efficient description of everything that jointly maximizes what's sometimes called compactness or simplicity and empirical adequacy. So empirical adequacy is just that, you know, if I say, what will I find if I look at this particular space-time region? It should give you the right answer, or most of the time give you the right answer, or give you something close to the right answer. So there's a little bit of, you know, you can be a little bit empirically inadequate if it helps you maximize the other parameter, but you still have to be able to accurately describe what's happening in all of these various space-time regions. And this is sort of supposed to be jointly maximized with, but of course, in tension with simplicity. So it must be as simple a description as possible. So you can't just give like the full, the most empirically adequate description would just say exactly what happens at every single space-time point. And it would be sort of maximally long because you were super thorough. So the idea is that there are regularities in the ways in which things are distributed through the space-time regions. And we take advantage of that. And that's why we can get more simplicity or less simplicity, even while maintaining the same amount of empirical adequacy. So we want to take advantage of those regularities in the pattern of distribution to get more simplicity without giving up empirical adequacy. So there are, of course, different ways in which you can balance these two different desiderata, in which you can emphasize simplicity over adequacy or vice versa. You can even hold fixed empirical adequacy and have different ways of understanding what it means. Is this version simpler or is that version simpler? Is it simpler if it has fewer variables, but more laws? Or is it simpler if it has more variables, but fewer laws? And there's other concerns about our epistemic access to such laws. So there's no reason to think that they have to look anything like our best current science. So it's not entirely clear in all of the cases what it is that the neo-Humean accounts of laws, what we could learn about them from anything that we're doing in the sciences. So it could be that none of the laws that we're doing in the science will turn out to be part of that most efficient and empirically adequate description. All right. On the other hand, you might want to do more with the modality. So insofar as something isn't just an accident, isn't fully contingent, then there's got to be something to it. So there's also, I picked the year 2000 and it was just a really good year for papers. There's also an account of laws in terms of several different dimensions. So this is a sort of pragmatist account. So instead of rejecting laws as unsuitable for biology or admitting biology lacks laws, what she does instead is redefine laws. No, really, laws never did look like what Hempel and Oppenheim told us. Instead, they look like this. And then you have one account of laws that works both in biology and in physics. So in the case of mechanisms, you have mechanisms in some fields, but then far fewer of them, if any, in fields like some of the sciences or some of the physics, especially more fundamental physics. This view allows you to then say things that connect the different sciences more to each other because you have a common view of laws that go with it. So the parameters that she offers are different ways of codifying specific kinds of variation in necessity. So instead of saying, is this an accident or is it necessary? You know, yes, no. She rejects that kind of dichotomous approach and said, no, there's different degrees to which things can vary in their necessity. And the first set of parameters that she describes are what she calls ontological. So they're things that really are in the world itself, one of which is stability. So how stable are the conditions under which a particular regularity holds? So you can have some regularities that hold very, very stably. So ones from, say, relativity are going to hold very stably across spacetime. But you can still use, for instance, Galileo's law of odd numbers if you want to. It's just the conditions under which it's stable include adding the specification very close to the surface of Earth. If you go too high, it's not going to work anymore. So you can have variation in the stability of a generalization that sort of lays out what the conditions are under which it holds and the conditions under which it ceases to hold. So then you have a generalization that gets you somewhere, even if it doesn't get you like the universal version of it. Another ontological parameter is strength. So sometimes two variables might be extremely strongly connected to one another or weakly connected. So for instance, you could have extremely high strength for a law that is extremely low stability. So it only holds under these very particular circumstances, but when it holds like rock solid. So there's a lot of cases where you're trying to come up with laws that behave like this in physics, where you have very, very special kinds of experimental setups that you have to have exactly right. And if you get them exactly right, then those are the conditions, the very narrow, unstable conditions under which it holds, but it holds with a really high degree of strength. So that sort of answers a lot of the concerns that people like Nancy Cartwright have raised over the years, when you can have high strength but low stability. In cases like biology, you might have things with low strength but higher stability. So you're not using artificially generated lab circumstances. You've just got boatloads of stuff happening in the wild. And so all of the strength of the generalizations is lower, but they're a lot more stable. You can generalize across a wider range of circumstances. But she also adds additional parameters. And this is part of what makes it a pragmatist account of laws. So degree of abstraction. Sometimes there are patterns or regularities that only become apparent when you ignore some of the details. So this actually also holds in physics. In order to get to the laws of the Newtonian theoretical system, for example, you have to ignore, especially in the original sort of presentation of it, you have to ignore things like thermodynamics. But that's a really salient part of most people's everyday experience. So a degree of abstraction, something becomes more abstract when you ignore more about the physical details in order to pick out something else. So there are some regularities that you only see when you ignore certain kinds of microphysical details. And of course, there's simplicity, where there might be simpler versions of laws that you still call laws. And they're laws because they only work in certain contexts, but when you're in that context, you really should know this because it's incredibly handy. And this comes out in a lot of textbooks too. So especially in physics, there will be something that's called a law of refraction. And it's not because refraction is this deep fundamental part of the universe. It's because if you're doing things in this whole region of optics, which you are if you're working in optics, then this little mathematical relationship of variables is so handy that we're going to give it the word law to sort of indicate to you, no, really, you should pay attention to this one. So in that sense, law is kind of a term that you give the stuff that's so useful that you're going to want to sort of keep track of it and keep using it. And then finally, she adds cognitive manageability. This includes computational tractability, but it also includes human comprehension. So if there are laws that we can't really grasp, then we can't really use them for anything when we're doing science. So we have to have some sort of ability to understand what's going on in order to deploy something in our reasoning in a certain sort of way. So that's part of what she's adding as if you have different variations of how you could express some laws, then you should prefer the one that has, easier traction for the humans who have to use it. All right, so To sort of contrast, you can see hopefully a difference here between what might be called top-down versus bottom-up approaches to generalizations. So the top-down ones are like the covering law. So you've got this true universal generalization from which you deduce individual things that are covered by that true universal generalization. So from the top, you go down. On the other hand, you have something in this case that works especially well in biology from the bottom up. So anything that generalizes, if I can say anything that's true of this species, but also that species, even if I can only say it of those two, then that's an advantage. I've just sort of improved my position than when I had to say separate things about these two different species. So anything that generalizes, even if it's a highly constrained or highly conditional or highly localized generalization, still is better than what you had before you figured out that you could generalize it. So you sort of build up from the bottom in a more sort of patchwork way. And then you might suddenly discover, oh wait, if I change my degree of abstraction, I can suddenly cover anything that's a mammal, for instance, with this generalization. And then you're sort of often running with respect to building things that are more general from the bottom up rather than from the top down. All right, so the other thing that goes into this, and that is especially important in the non-physics sciences, is that it's not always that there is some like, you know, aha, wow, look at that simplicity kind of thing that is what we're really after. So what Kepler and Galileo were doing just isn't what we're doing when we're doing biology. Sometimes the whole range of complexity is exactly what we want to dig into. And part of the task is just figuring out, okay, what's the best way to categorize this complexity so that we can describe it accurately in order to sort of get a handle on all of the different ways that things here can be. So you want to sort of exhaust all of the phenomena descriptively. So what are the kinds of parameters along which things can change or vary? And that's not the same as just saying there's a single underlying regularity with a simple description. So you might get a more simple, I don't know, taxonomic structure out of it, but it's still for tackling the complexity that you're not trying to make go away. You're trying to sort of own it. So this is a way that kind of goes in the opposite direction from what we saw before, where we started with phenomenological laws, and then you were moving towards simpler and more unificatory ones with some sort of underlying, more simple regularity. In this case, it's going towards more sort of concrete and situated generalizations. So you have a generalization and you take it as far as you can until you discover that you can't anymore. And then you figure out what it was about the circumstances that made it stop. All right, so this brings us then to the part where we're going to compare all of it. So laws, mechanisms, and causation. Mechanisms have proven to be extremely useful in many sciences, and they're really especially useful when you have scientists who are working on different parts of the same very complex phenomenon. So if you have a bunch of scientists who are working on how the mouse is able to navigate the water maze all the way down to the cellular level, subcellular level, then what you need is a way for them to coordinate their results, and the mechanisms provide a very effective way to do that. So you can unify your results into the single complex mechanism rather than, you know, unifying different phenomenological laws into a simple law. So it's not simple, but it's definitely a strategy for unification. Causation has displaced a lot of the work that we thought laws were supposed to be doing for us. And so it looks like if there's a place for laws, it's, you know, really small compared to what it was before. But that actually fits well into, I think, the historical trajectory that we started with, where laws were supposed to be the outer bounds of possibility. And then there were lots of things that could happen that were all compatible with the laws, and the laws aren't supposed to tell you which those are. So you shouldn't have the laws of physics telling you anything about like what the particularities of evolved species on Earth actually look like. That's just not the place of laws historically. So the rest of those details, like what does it actually look like, are supposed to be settled by something that wasn't laws. That's something more specific and more comparatively contingent, even while it doesn't have to be fully contingent. So, but there's still views of laws here where they're playing a role in representing gradations of necessity. And the gradations here are not mere probability. So there's things that can be necessary without just being highly probable. So they're less than universally true, and yet they're more than mere accidental coincidences. And all right, and that takes us to the end of this video. If you have any questions, further comments, if you would like any of the references that came out or that were mentioned in any of the videos, or if you would like to follow up and hear more about any of these debates, please let me know. My email is below. It's, please notice, handerse@sfu.ca. All right, thank you.